In this example, the random variable x capital has a probability function p x capital equal x, where when x is 1 and 3 multiply kx, and when x is 2 and 4 will be k multiplied by x minus 1, where k is a constant and we need to find the value of k. So we'll start by creating our table for when x is 1, 2, 3 and 4. So this is how it is populated. So we will have the 1 and the 3 where we would have its kx, and we would have the 2 and 4 where it is coming from k multiplied by x minus 1. So now we populate the values of x. That will give us for 1 is k, for 2 is k, for 3 is 3k, and 4 is 3k. To find the value of k, we will add all the probabilities in the form k equating to 1. So that will give us k plus 3k plus 3k equal 1, and then that would give us 8k equal 1, and then the value of k in this scenario will be 1 over 8. Now for part B, we need to find the probability of x capital being bigger than 1. So we'll start by creating our probability distribution. So in this scenario, we would have for 1, 2, and 3, and 4, and we would have in this scenario using probability mass distribution, we would have because we have 4 possibilities, we would have the k, the 8th over 4, so that would give us 0.125, and for again when we have 2 over so 1/8 over 4 over 2 over 4, that would give us 0.125 also, so because they are a fourth of each. And then we would also have for the third, which is 3k, so we'd have 3 multiplied by k. So to simplify this, we would have in this scenario it comes from multiplying the number of x, so let's say 1 or 2 or 3 or 4 multiplied by the value of k. So this is how we find the values here. And now to add these values to get the probability, so we would have 0.125 plus 0.375 and 0.375, because this is repeated and we only take it once. So now in this scenario, that would give us the 0.875 as the value being bigger in terms of the probability of x capital being bigger than 1. And this will be our answer for this question. In this example, the discrete random variable x capital has a probability function when probability of x capital to the x equal, where 0.1 when x is minus 2 and minus 1, and beta when x is 0 and 1, and 0.2 when x is equal to. Find the value of beta. So first we can create a table to populate the values from the negative to the positive, and we can populate the table as shown here. So we would have minus 2 is 0.1, minus 1 is 0.1, 0 is beta, 1 is beta, and 2 is 0.2. So for us to find the value of beta, we can add the probabilities that would give us, and equating them to 1. So that would give us 0.1 plus 0.1 plus beta 0.2 equal 1. So that would give us 2 beta, and we have 0.2, we move it to the other side, 0.2 plus 0.2 will be 0.4, so we move it to the right hand side. That would give us 1, take away 0.4, so that would give us 2 beta equal 0.6. In this scenario, the value of beta will be 0.3. So this is our answer for part A. For part B, construct a table given the probability distribution of x capital. So in this scenario, we create our table, which is we found the value of beta, so we populate the values of beta. So that this is how our table would look like after the values of beta are populated. And then for part C, we need to find probability of minus 1 being smaller than or equal to x, and also x smaller than 2. So for us to find this probability, we would have the probability we would have the 0.1 plus 0.3 plus 0.3. So these are the main the values that we will add, and we will not look at the value of when x is 2. So that will give us the addition of these probabilities will give us 0.7, and this will be our answer for part C. In this example, a discrete random variable has a probability distribution shown in the table. So we can see the table on here, where 0 is quarter minus a, and 1 is a, and 2 is half plus a. We are asked to find the value of a. So we will add the probabilities shown and we'll equate them to 1. So we'd have quarter minus a plus half plus a equal 1, and then we'll try to add the a's together and add the fractions together. So that will give us 3 over 4 plus a, because the positive and negative a's will disappear, and we will be left with 1a, and so we would have 3 over 4 plus a equal 1. And then to simplify that further, we would have a to be equaling a quarter, and this will be our answer for this question. In this example, the random variable x capital can take any integer value from 1 to 50. Given that x capital has a discrete uniform distribution, find first probability when x capital equal 1. So we will start by looking when populate x is 1, we would have 1 over 50 because we are taking it from 50 values, and since each of the 50 individual outcomes is equally likely. So this is what we're looking at for part A. For part B, when we have x is bigger and equal to 28, so we will look at scenarios where in this scenario when it's bigger and equal to 8, we take it from the total, which is 1, and we take this 27 out of it, 27 out of 50, because these are the possibilities that are out of, so because we're mainly focusing on the bigger than and equal to 28. So that would give us 23 over 50 as the probability for x bigger and equal to 28. Now we look at probability when 13 is smaller than x and x is smaller than 42. So we're looking at this range. So in this scenario we would have probability, so we can flip this probability to be 14 is smaller and equal to x, and also x is smaller and equal to 41, so it's almost a little bit bigger than 13 and a little bit smaller than 41. So in this scenario we're looking at the range of 28 over 50. Okay, and that can be simplified to 14 over 25, and this will be our answer for part C. In this example, a discrete random variable x capital has the probability distribution shown in the table. For part A, find 1 being smaller in the scenario smaller than x, and x being smaller and equal to 3. So for part A, we will look at when we have 1 smaller than x and x is smaller and equal to 3, we can take the values when x is equal to 2 and add it to x equal to 3, so that will be half for 2, and for 3 is 8. So we add these two values, that would give us 5 over 8, and this will be our answer for part A. For part B, we'll take when x, the probability when x is smaller in this scenario than 2. So we will look at when x is smaller than 2, so that will be when x is either equal to 0 or x plus x equal to 1. So this is where we're looking at 8 plus a quarter, and that would give us 3 over 8 for part B. For part C, what we're looking at when x is bigger than 3, so the probability in this scenario will be mainly looking at values bigger than 3, so we can't see any values bigger than 3 here, so that will mean that the probability will be equal to 0, and this will be our answer for this question. In this example, a biased coin is tossed until a head appears, or it is tossed 4 times. So if probability of head is equal to 2 over 3, write down the probability distribution of S, the number of tosses in a table form. So in this scenario, we can create a table, and we're looking at 4 tosses in this scenario. So this is how it will look like. So we have 1 first toss, the second, third, and fourth. So for the first one, we are told it will be 2/3. Now for moving forward from there, it will be either a third multiplied by 2/3, or we would have a third, and because we're looking at the multiple scenarios that we have here, or we have a third multiplied by a third multiplied by 2/3. For the 3, that will give us 2/27, and for 2 is 2/9, and for 4 we would have 3/3, third multiplied by a third multiplied by a third, and then multiplied by 2/3, plus another third multiplied by 3 other thirds. So that would give us approximately 1/27. Now these values are extracted from the number of tosses in this scenario, 4 times or 3 times, and of course multiplied by the factor of 2/3. For part B, we need to find when the probability when S is bigger than 2. So in this scenario, we're mainly looking at the third and fourth tosses. So in this scenario, we would have 2/27 plus 1/27, and that would give us the answer to be 1/9. And this will be our answer for this question.